we're very pleased to have two gentlemen from two different companies.
Two different companies.
Yeah.
They work together.
Offering an interesting technical program, New Techniques to Save Historic Masonry Structures, presented by Andrew Markopoulos and Donald Harvey, two experts in non-destructive testing and engineering and preservation of existing historic masonry structures. Andrew, after many years in the financial services industry, decided to change career path and became the primary project development person for the Mid-Atlantic region for Masonry Solutions International, a masonry and preservation enhancement company located in Maryland. He graduated from Towson University with a BS in Business Administration, Marketing, and Finance, and his financial services work involved managing a $100 million portfolio, and he's headed several small businesses and been a consultant on business development strategies. Donald Harvey is an Associate Vice President at Atkinson, Noland and Associates in Boulder, Colorado, so welcome from Boulder. And it's an engineering consulting firm that specializes in evaluation and repair of historic masonry structures. Before joining them in 2006, he worked as an investigative engineer at West Janney Elstner in Dallas, Texas, and they're a nationwide forensic engineering firm. Mr. Harvey has a Bachelor of Science degree from the University of Texas at Austin in architectural engineering and a Master of Science degree in civil engineering. He has authored several papers relating to non-destructive evaluation of structures, historic preservation, masonry material testing and evaluation methods for existing buildings, and he serves on several ASTM committees, that's the national standards for all kinds of things related to masonry. So our speakers have also collaborated on several historic structure projects, and I'm sure we'll see some interesting case studies today. And please let's welcome Andrew Markopoulos and Donald Harvey.
Thank you. I just want to grab a few of the packets that I had made for you guys. You already have them, that's great. If not, what you'll find there is kind of a recap of what we're going to be talking about today. A case study or two, I think there's one in there, and some information about what it is that we offer as far as products and the services that we offer. And I always preface my presentation with a quick little commercial. Masonry Solutions has been in business for over 20 years, and our focus is on providing the industry with solutions to taking structures that are failing and bringing them back to life. And we'll be talking a lot about what we call CIF, compatible injection fill, that we use to actually inject ground injection into failing masonry walls, along with a lot of anchoring that we do that would be happening at the same time, possibly, depending on what the project calls for. So some of the products that we do offer are proprietary, and we will get into those as well. But today I just want to briefly go over what the description is. The course description: New Techniques on Saving Historic Masonry Structures. So if there are any questions while we're going along, we'd be happy to answer them as well. So the learning objectives today, of course, if you're AIA, if you're an architect or an engineer, you will receive credit today. And we're after identifying and discussing new techniques for non-destructive masonry evaluation, identifying and discussing new techniques to repair structural inadequacies in historic masonry structures, and understanding the compatibility issues. You'll hear a lot about compatibility today. It's very important in our business to always understand the what is at hand and the issues that we're up against when it comes to revitalizing structures. Being qualified to identify and specify new techniques to repair structural inadequacies of historic masonry. So these are the things that we're going to be covering today, and we'll be kind of doing a tag team throughout the session. So Masonry Solutions, we are a worldwide technical services and manufacturing firm providing customized approaches for the rejuvenation of historic masonry. And it's important to understand we have an affiliation with Atkinson Nolan, who Donald is with, and they are the investigative engineering firm with the offices in Boulder and New York as well. And we work together with them to come up with solutions for these structures. What we see here, and we'll get into some of the more detailed case studies towards the end of the session, but just to kind of go through some of the more notable projects that we've worked on over the last 10, 15 years. The upper left-hand corner, what you see there are the pump stations in New Orleans. As we know, 10 years ago, Katrina took a toll on New Orleans, and the pump stations were in danger at the time. They continued to run. We were called in after the hurricane to reinforce these pump stations so that if there was another hurricane, to protect against wind damage in the future. So we had gone in and structurally reinforced many of the pump stations there. Down in the lower left-hand corner, we have the New York City Hall, which is a very famous structure and has very sensitive, the rotunda is a very sensitive place within the building. It was subjected to a lot of movement. There was a subway station nearby that was causing a lot of cracking that was taking place within the building. Upper right-hand corner, West Point, they had water penetration issues, and some of the things that we do, you'll see we are not waterproofers, but some of the things that we do, in fact, will help situations like that. Lower right-hand corner, we have the University of Missouri, and that's quite an extensive case study we'll talk about a little bit later. And I'll turn it over to Donald right now. I'll come back in a little bit to tell you more about Masonry Solutions.
Thank you. I always like to have some feel for who I'm speaking to because I'm an engineer and I tend to use engineering words and phrases and so on and so forth. So if I could do a very quick survey, and I don't know all the classifications and categories that might be in the room, but I know there's at least one architect in the room, so I'm going to ask that first. If you're an architect or a designer of some sort, raise your hand. Well, we have exactly one architect in the room. Okay. Any engineers like myself? Of course not. That would be too easy. How about contractors, restoration specialists, that sort of thing? Great. Suppliers? Any suppliers? Great. Building owners, property managers, that sort of thing. All right, who am I missing? What category have I not named? This is a very diverse group. Yes.
I'm a historic homeowner.
Historic homeowner. Okay, great.
With masonry issues.
Great. Anyone else that I missed in putting you into a box? There's lots of different boxes, clearly. So, great. Well, especially since there's no engineers, I will try to refrain from using too much technical jargon. But if I do, I apologize. I can't help it. So this is one of the kind of guiding philosophies that Atkinson Nolan and Masonry Solutions have had, and I think what should be a guiding philosophy in the preservation industry, which is that really any masonry structure can be saved. It's just a matter of degree. We've been involved with many projects where the initial evaluation was we need to rip down this building and start over. And we're using a lot of new techniques and methodologies and materials, etc. We've been able to save quite a few buildings, and that makes us really happy when we're able to do that. We're also guided by a few preservation principles that might be familiar to some of you out there. We like to intervene as minimally as possible. This is related to the compatibility word that you'll hear a lot. Our philosophy is to try to work with the structure, to have it do what it was intended to do, and just do it better, stronger than it did before. So we want to intervene as minimally as possible. We don't want to interfere with any future repairs. We like to be reversible when we can be, and certainly we want anything we do to the building to be compatible with what's there already. We don't want to disturb the historic fabric. So these are some kind of overall guiding principles of what we do. So before we can use wonderful new technologies and methods for strengthening, we have to know what we're up against, what we are trying to repair, what's there. If we're going to be compatible with the existing materials, we have to know what the existing materials are. And that involves oftentimes some investigation of the existing masonry. Most projects that we get onto, we can't look at a nice set of drawings and look in the structural notes and find what the F prime sub M is for the building. We can't look at a specification book and see who provided the brick or stone and mortar and so on and so forth. Most of the structures we would deal with probably didn't have a set of drawings, or if they did, they were pretty rough. So although we've seen some beautiful, West Point, by the way, one of the projects in the chapel at West Point, there were some beautiful hand-drawn original drawings that we had for that building, and they were just wonderful to look at, but still didn't have masonry properties that we needed for engineering purposes. So a lot of times we use non-destructive testing, non-destructive evaluation, and other means to try to determine what's there, and that's the first step in our process. We'll go through a few of the methods that we use. We have some pretty fancy, expensive toys that we can use. A lot of people in the industry have similar types of toys to evaluate what's there. But the first thing is still the most valuable, just our eyes, looking at what's there, looking carefully, looking into behind, sometimes with the assistance of a borescope so we can look inside of walls. But looking at masonry is still the best way to get a feel for what's there, what the configuration is, where are the issues, what needs to be strengthened and what doesn't. So we'll talk a little bit more about some options that we have. One of the most challenging things is a problem that we've faced in the industry for I guess about 100 years, and we still haven't come up with a great solution for, and that's determining how hard the mortar in a wall is. We do now have the ability to sample mortar and do petrographic analysis, chemical analysis, that sort of thing, to determine components, but oftentimes in the field we just simply want to know how hard the mortar is. And you'll see people like me sticking our fingers in joints sometimes, rubbing it with the soft part of our finger. A lot of sand lime mortars with no Portland cement at all. You can brush off a little bit of the mortar with just the soft part of your finger. Sometimes when the mortar gets a little bit harder, we'll take a key or screwdriver or a pick and scratch at it and see how hard it is based on that. And then if it doesn't even scratch with that, we know it's pretty hard Portland cement mortar. There is a slightly more scientific tool. This is called a pendulum hammer. It's similar to a Schmidt hammer, if any of you have ever used that type of device with concrete. It's a measure of surface hardness. Some people also use Windsor pins, which are used in concrete hardness testing as well. But this device has a pretty good record, or a pretty good level of accuracy for distinguishing between very soft historic mortars, but not so good once the mortars get really hard, type S, modern Portland cement mortars. So there was an attempt to get an ASTM standard put together for actually using that, and it never happened, unfortunately. Someone at our company was trying to do that. Borescope and fiber optic. Again, this is essentially a visual tool that we use quite a bit to look at subsurface conditions. This is a video scope, just a simple type of video scope that we use quite a bit. A lot of what we really want to know about historic masonry walls is what's happening beyond the surface, not what we see at the surface. In this case, We're looking into some voided cavity, and this is a helical anchor that has been put through the exterior wide of the brick, and it's not engaged with anything behind it. So that's an important type of thing to know as well. So, borescope and visual survey is still very valuable. Ultrasonic pulse velocity, I won't get into too much. It's basically a tool that we use to look for gaps and voids. One of the projects that we used UPV on recently was a large, about 10 foot by 10 foot by 10 foot cube of marble that was to be used for a sculpture. And the sculptors wanted to know before they started sculpting whether or not there was any crack or delamination somewhere in the middle of that block before they got started doing a rather elaborate sculpture.
How big did you say it was?
10 foot by 10 foot by 10 foot. It was going to be a lion, actually.
So it's 100% guarantee there was going to be a lion.
Yes, but where it happened was really important because a lot of that 10 foot was being carved away. So yes, right in the very center of it would have been really bad, and it was actually usable. So they were pleased with that. So that technology is good for kind of finding cracks, voids, openings within things. A similar technology can be used to find continuity as opposed to voids. Things like headers, intermittent headers between wides or layers of walls. We can kind of tap on things and listen on the other side to see where that energy gets through. So one of the technologies that we use most, actually, really almost on a daily basis at our firm is ground penetrating radar. Sometimes it's called surface penetrating radar. Sometimes it's called microwave radar. No one really knows what to call it, I guess. All of them kind of sound a little bit scary. The most scary thing that it's called often is it's often called X-ray. People will say, "Can you come over and X-ray my floor?" And we say, "No, but we can tell you what's in it using GPR. We can look for reinforcing and voids and gaps and so on and so forth. And we will do it without exposing ourselves to radiation, which is certainly my preference. But GPR basically uses electromagnetic waves. They're kind of in the range between microwave and radar that's used for aircraft. And we bounce off of things like voids, etc. I believe there's a video here on the next slide that gives you a little bit of a feel for kind of how that looks, but it's that's actually a little bit less powerful than your cell phone in terms of the amount of radiation, quote unquote, it emits. So very safe. We don't have to evacuate things to do this. And a lot of what we use it for, since we deal with masonry a lot, is we look for voids and openings in collar joints. We look for embedded metals, anchors and ties, and as we'll talk about in a little while, in injection projects where we're actually trying to fill voids and gaps in masonry walls, we'll use it as a quality control measure to see if gaps and voids have been filled. Yes?
Why do you, are gaps and voids, are you thinking moisture mostly?
That's a good question. Sometimes there's a few different reasons, and we'll talk a little bit more about that when we get into the injection process. Sometimes we're filling gaps and voids because of moisture infiltration. Sometimes to get structural continuity between layers of bricks. Sometimes because we're going to add reinforcing into a wall and we need it to be solid before we install reinforcing. So good question. One of the things that an example of something we use microwave radar for pretty successfully is locating what we sometimes call hidden headers or diagonal headers. Wow, that's really washed out. I'm sorry.
I can barely see.
But if you look in plan view, some
Visible. You can see.
some walls have, rather than having headers that are turned 90 degrees, we only have one architect in the room, so I can say this without being too offensive. Some architect at some point in history decided seeing headers was unsightly and we should hide them, and therefore we have these diagonal or hidden or queen's closure headers, however you want to refer to them. these types of headers unfortunately don't perform very well. They don't engage nearly as much of the masonry on each side, and we've unfortunately had some instances where wise of masonry have actually peeled apart with this type of configuration. So this is a GPR stand. This is what we look at when we use the GPR technology, and these little bumps here, oh, our arrows are misplaced. Those little bumps there are the tips of the headers. So we can actually see those subsurface without having to rip the wall apart. But if you do rip the wall apart, which I don't think we did in order to find these, in this case, this is what they kind of look like. You can see they're oriented at about a 45-degree angle and don't really grab that much of the other masonry. So sometimes we need to supplement. Again, microwave radar or GPR used in this case in a dome with some coffers to locate where those coffers were, how thick the masonry was surrounding those coffers, etc. So lots of applications. Another technology we use is infrared thermography. Infrared thermography is really good for locating moisture and voids primarily. So conditions have to be right for infrared thermography to work. Usually we need to have direct sunlight on a wall for it to work best. But it's a useful tool, and it gives you a picture, which is really nice because it's easy to interpret. Walmart has actually gone to 100% infrared thermography quality control on their CMU mason and their concrete masonry stores because you can see whether or not the grouted cells are full. So they can actually tell if there's any mortar fins, anything that's prevented grout from filling up where it's supposed to be just by taking pictures of the wall. So it's very efficient and pretty easy to interpret. This is a slightly different example where we were dealing with a smokehouse that had high salt content, and eventually some poultices were used to draw salt out of the masonry that was damaging the masonry at a historic smokehouse. And here we were primarily looking at moisture content with infrared. So in addition to some of the non-destructive techniques that tell us about what the configuration is, a lot of times we as engineers want to know how strong things are. That's a pretty important property of masonry for us because we want to design buildings that stand up, and standing up usually has something to do with strength properties, both compressive strength, shear strength, lots of different types of strength. So we have a number of different types of testing that we do related to strength of masonry and strength of anchors embedded in masonry as well. Here's a shear test, some anchor tests, and we'll talk more about this. This is called a flatjack test. Flatjack test is essentially a compression test of masonry in place. What we do to do a flatjack test is cut a couple of slots horizontally into some bed joints, insert stainless steel bladders into those slots, mount some LVDTs to look at how much this brick is moving, and we inflate those jacks to squeeze the masonry between it. What this allows us to do is get a stress strain curve, a compression test result. Sorry, that was an engineering term there. I'll try to avoid that. We get how strong it is in compression while everything's still in the wall. When we're done with the test, these joints can be repointed with mortar and it's like we were never there. If you try to take some sort of sample out of the wall and bring it to a laboratory to test, in a lot of cases, especially with historic masonry, by the time you got it off the truck, you would have individual bricks that were no longer connected together. So trying to take a specimen from a wall and bring it to a laboratory usually isn't practical. So this is an alternative, and engineers really like having that information when they're doing their design. We mentioned moisture earlier. There's actually a quantitative way to measure moisture infiltration through masonry walls. There's a test called the STM C1601, and sometimes we call this test the storm in a box test. I think there may be a better picture later, but this is a 3 foot by 4 foot box with a clear plexiglass exterior that has a spray bar that sprays the surface, and air pressure is applied to simulate a very strong wind, about a 56 mile per hour wind actually. So it's intended to simulate a very heavy storm, high wind and high rain storm. And what's done is essentially the water supply, which here is in an elegantly equipped trash can. That trash can sits on a scale, so we measure the weight of it, and we see how much that weight changes over time, and we can plot that. In this case, this is actually a before and after test. We just did one of these up in New York on some lofts on Park Avenue as well. And the before test is as the wall was. The after test is after compatible injected fill injection into the wall. And this line, which almost looks horizontal, was the post-injection, and this was the pre-injection. Usually we see 90 to 99% moisture infiltration reduction after injection.
So, excuse me, that box is actually sealed against the wall then?
Yes, there's
So
actually...
you're collecting all the water that didn't penetrate the wall.
Correct. There's a gasket around, and this you may not be able to see, but this right here is a little drain in the bottom that goes back into the trash can.
And the rest of the water that's penetrated is in the cavity somewhere.
Right. There's another type of test. There's a laboratory version of this test called STME 514. In that test, you collect both the water that runs off the face and any water that's running down the back surface, and you measure both. In this case, in the field version of the test, usually it's not practical to collect the water on the back side, so we just get information about how much gets past the surface. Masonry injection, even though we think of it often as a pretty new technique, we use some new fancy chemistry to do it. It's actually a pretty old technique. People as far back as 1886 were injecting cracks in masonry with cement. And that's essentially what compatible injected fill and other types of technology that we'll talk about are doing. It's a pretty old concept. We hope that we do it a little better than we did in 1886, but I guess you can be the judge of that. So I think we have an example of this that you can actually put your hands on. When we talk about compatible injected fill, what that means, what we're talking about is a grout material that is extremely fluid that can be injected into an existing masonry wall in order to make it solid for various purposes, as we've already kind of alluded to. If we're going to put something into an existing historic masonry wall, we are very concerned that it be compatible with what we're putting it into, that it have very similar properties in terms of moisture absorption, vapor permeability, structural stiffness, etc. And we'll talk a little bit more about that compatibility. This, I don't know if you can make it out on this projector very well, but you can kind of see the edge here. This is original mortar, and this is original mortar, and there's a little bit of original mortar in here. The slightly wider material in there is compatible injected fill. This is a core that was taken out of a wall that was injected. And you can see how well it fills very small nooks and crannies. We'll have some other demonstrations of that too. So my firm at Atkinson Nolan, I'm sorry, yes?
So if you have a wall with old lime water, which is fairly flexible, you can make the grout work with that level of flexibility in the wall as opposed to a Portland cement wall?
Absolutely, yeah. We on the projects that we work with, typically we will custom design a mix for a specific project, or at least a kind of a range of strengths. We've done actually at some of the pump stations, which we'll talk about more in one of the case studies, the compressive strengths of those walls were 250 to 400 psi compressive strength, which may mean nothing to most of you in this room, but kind of a normal concrete is 3,000 psi, so we're talking about a tenth of a normal concrete compressive strength. Modern masonry would be usually 8,000 psi or so strength, even higher. So very, very sensitive, delicate masonry, if you will. And so our mixed design was, the compressive strength target was between around 500 to 800 PSI. So yeah, there are people who make very flowable, high cement content materials that are intended for other purposes that are, 7,000 or 8,000 PSI. We don't put those kind of materials into walls that are only 300 PSI. That's not the way we do things. We'll talk about it a little bit more. This was some of the work that was done to develop CIF. We actually built some walls and trial tested them. We did various types of testing on the materials as well. Here's one of the reasons, one of the engineering reasons that we are so concerned about compatibility. If you insert a very high strength material, whether it's a very high Portland cement content injected material, or in Europe, you may have seen or heard of people injecting the rubble in the middle of their walls with epoxy. That's actually a pretty popular repair method in Europe, is injecting high strength epoxy into the middle of lime mortared walls. That creates some really high stress concentrations right in the middle of that wall that weren't ever intended to be there, and that can have some nasty consequences from a structural standpoint. The other thing that this does for architects in the room and maybe others who've had issues related to this is epoxies usually make very effective vapor barriers. So when you install epoxy into the middle of a wall, you're putting a vapor barrier right into the middle of that wall. That may be exactly where you would want a vapor barrier to be, and it may be great and fine, but oftentimes it's not where you would want a vapor barrier to be, and it can create problems with condensation, etc. So our preference is make the material that's injected similar to what's around it, therefore stresses are distributed evenly, the wall's doing what it was originally intended to do, only better. We won't talk too much about that. A lot of the walls that we come to look a lot like this when we get to them. We've got sporadic headers. The headers that are there are cracked. There's poor connectivity between the withes, the layers of the masonry, and structurally this wall is kind of a mess. But to us this looks like a wall that is ready to be strengthened. It's certainly salvageable.
It was ready a long time ago.
It was ready a while.
That's the project that I hope I have common sense to walk away from.
So we'll get into what the injection procedure looks like here. There's a video that will kind of demonstrate that. But these are very flowable materials. I usually say, wow, that's super washed out. I usually say the consistency of compatible injected fill is similar to kind of a thick paint. I used to say milkshake, but milkshakes have gotten really, really thick sometimes. So it's actually thinner than a lot of milkshakes are these days. I'm going to see if I can get this brightness down so you can actually see what's going on.
So do these walls need to be formed up to support them from hydrostatic pressure or blowout and things like that?
That's a good question. So we actually will oftentimes support against the hydrostatic pressure using, you have your heel fix today, or, oh, sorry, that's a brand name, helical tie, generic helical tie. So that's one of the tools that we use so oftentimes we'll tie the wides together using helical ties so that outward fluid pressure doesn't bow or collapse or otherwise damage the wall. So that's one of the tools we use. So you can see the first step is drilling some small diameter, usually 3/8 to 3/4 inch holes in mortar joints. A small nozzle is used to inject material through those holes into subsurface voids and collar joints and cracks, etc. Those holes are plugged. You'll see here in a moment. I think the next video is a real world. Okay, so this gives you a good feel for how fluid the material actually is. This is the nozzle he's injecting into the wall. These are little plugs. You can kind of see some there. I think you'll get a better visual on this in a moment. So he's injecting into a hole here, and material is coming out of the wall there. I don't know if you can see how quickly it's flowing out there, and I may have made it too dark now. But yeah, it's coming out here, and so on and so forth. So this is an extremely fluid material, and one of the nice things about this method of injecting is if you're injecting the wall here and it's coming out here, you have a pretty good feel that the wall is full between those 2 points because the material is flowed between those 2 points. So it has a lot of nice quality control features in that regard. And then we actually use GPR oftentimes to scan before and after and determine whether or not we filled things up the way we'd like to. And this is a picture from actually the very first project that Masonry Solutions and Atkinson Nolan did together using a compatible injected fill material. This was an apartment building with concrete block and brick that the structural engineer had designed as a composite wall, meaning the block and the brick were intended to be grounded solidly together, and both were needed in order to handle the loads that were imposed on the structure. The way it was built was as a cavity wall where this was left completely empty, so that the brick and the block were independent of one another, and structurally that didn't work. And the initial instruction to the general contractor was to rip the building down and start again, which was a multi-million-dollar type of request. So Atkinson Nolan and Masonry Solutions worked together to develop a material where we could, as Wayne likes to say, put the toothpaste back into the tube. That's essentially what we were doing. We were putting toothpaste into a rather awkward and narrow tube, and did this successfully. The building was able to remain in place and in service and function as it was originally intended. This was actually a fairly modern structure, not a historic structure, but actually most of our work since then has been on more historic structures. As I mentioned before, this is another GPR scan. It's just colorful because colors are more interesting. This shows kind of the before and after scan. Here you kind of see reflections off of various voids and gaps, and here those are solid, which is what we want to see. We've already passed around helical ties. That's one of the things that we use often in conjunction with injection. Once a wall is injected, the bond of the CIF material between wides does a great job of interconnecting wides, but while it's still fluid, it can actually kind of push wides apart, so we don't want that to happen. So a lot of times we'll use those helical ties, and there's other types of anchors that we'll use as well. Here's an example of some of those helical ties being installed between wides, and you can see in this case a collar joint here between wides, between layers of masonry is pretty wide open, and that's honestly very common. Oftentimes in historic masonry, the people who built the exterior wide of masonry weren't even the same people who built the backup. You have a face brick that was put together by masons with nice, tight, linear joints, and the backup brick is what was usually called common brick, and oftentimes it's laid rather haphazardly. You have joints that do this.
Those are the apprentices.
Those are yes. Apprentice is rather generous. I would call them laborers. They knew what a brick was because they were putting them in place, but that's about as much credit as they get for being masons. Labor has always been expensive, so oftentimes the connectivity between the exterior wise specifically and the interior wise is pretty poor in historic masonry structures. That's kind of a look down in a cavity at one of those joints. In addition to injecting big voids and collar joints, etc., sometimes in masonry we just have small cracks. The New York City Hall that we referred to earlier, many of the cracks at that location were relatively fine cracks, but significant both for structural reasons and for moisture infiltration reasons. And we can use compatible injected fill to inject even very fine cracks, similar to what those of you who've dealt with concrete in the past might have seen with epoxy injection of concrete cracks and that sort of thing. We can do that with CIF materials as well. So oftentimes what you'll see after injection is you'll see a little bit of residue, there's a little bit of a delamination, a little bit of a crack there between the mortar and the brick, and the CIF will actually even get into those very, very fine cracks because it's so fluid and flowable. One of the installers that we work with refers to this as the milk. You'll see the milk come out of the surface of the wall when you're injecting. And that's a good sign. That shows that it's actually pushing into all those cracks and voids. We're going to talk a little bit about anchors. I'm going to hand it off here shortly, but another relatively new technology that we have to restore, to strengthen, to rehabilitate historic masonry walls are internal anchors. And those internal anchors often are grouted into place, secured into place with CIF, and sometimes CIFs that are filled, socks that are filled with CIF that actually engage the masonry. Yeah, the fancy thing on the end is to splice bars together. If you can't figure that out, and that's all stainless steel. That's probably like $10 worth of stainless steel at least in raw materials.
Yeah.
Maybe 40.
I keep it under my car seat.
So these are the least expensive from us, right?
So,
When your CIF goes into the cracks, does it still have a bonding property, or does it act only as a filler?
no, and actually, when we do crack injection, we tend to do higher cement contents on those because we're more concerned about adhesive properties with crack injection. So, generally speaking, we're not putting enough material into the crack to create a whole lot of stress concentrations around it. We're just trying to glue it back together. So we do use more of the glue, which is Portland cement, to adhere things back together. So usually those are going to be somewhat higher strength materials because you have to get a little bit more strength when you add the adhesive back in. But yeah, the intent is for that crack to be like it was never there from a structural standpoint.
Okay.
Yes?
I have a 200-year-old house, and I just replaced the door and I replaced the jambs. When we got to the brick was so soft, I said, we in the carpenter said that there's no way we can put an expansion shield to hold the door jambs.
The door jamb, right.
And I don't know what we did, but what should we do?
That's a good question. So it's a little bit of a different scale when you're dealing with a house than when you're dealing with a larger, restoration project. What we could do if we were doing something along these lines, if there was budget and so on and so forth, is we could actually make those jambs solid using a CIF material and then anchor into it. For your purposes, probably it would be more practical to use something like a screen tube anchor to install anchors into a jamb. I don't know if are you familiar with what a screen tube anchor is? Okay, so a screen tube anchor is basically like it actually often is made of the same material as a window screen. And there's a little tube, a little sausage of this material. And the way it works is you put a really thick adhesive into the screen tube and then place it in the wall and push an anchor into it, and the adhesive bulges out from the tube in all directions and kind of engages with whatever's there and locks it into place, both with the adhesive action as well as the interlock that you get just because it's pushing into all the nooks and crannies and so on and so forth. And screen tube anchors we use a fair amount with historic masonry. We're not really talking about these. He doesn't like to hear this because he doesn't sell these. But for small residential applications, etc., this is something we deal with fairly regularly. It also doesn't hurt if you have a compatible mortar and you want to just parge everything, try to get mortar into the nooks and crannies as much as you can. Get a mortar parge coat that's relatively solid before you start anchoring. But if you're going to do that, don't go to Home Depot and buy the mortar off the shelf. You really need to have a mortar that's compatible with the mortar in the house. Unfortunately, we can see examples on this very building. I hope no one in here is responsible for this, but in this very building, there's some repointing mortar that's really hard that was placed over the historic mortar, and it's peeling off and creating some damage and so on and so forth. So you don't want to put a real hard Portland cement mortar over your existing masonry to anchor anything, but if you can find a compatible historic mortar, which I don't know, do you know if suppliers around here have a historic mortar? You guys sell one?
We carry 150s rated, and we have a MacLeod and
Great.
200.
So yeah, find a compatible. So what did you do? Now you posed the question, so now you have to fess up.
Coarse screw. We actually sort of like put glue on the screw and put it in. It's there.
When you
And the door hasn't fallen off yet,
buildings
right?
that were built with mud and horsehair and things like that. Which when I worked overseas, you'd have these buildings that were this wide, the walls, but they were extremely soft, and basically your anchor is just much longer. And you don't want to use anything that expands.
Right.
You
Absolutely
don't use
not.
anything that's expanded.
Yeah,
because
expansion anchors are the worst
you want
thing
to
to do.
distribute that load into the depth of the wall as much as you can, and that'll keep it from blowing out.
Right.
But the other way, the easiest way is to buy a pre-mixed mortar that's
Compatible, right.
Well, we also mix it ourselves. You know, you can mix the
Absolutely.
mortar yourself and adjust the quantities of cement and lime.
Absolutely. So you didn't do the horrible thing, especially if you, like you mentioned, almost always it makes more sense whenever you're attaching anything to historic masonry, use a lot of small anchors, not one big anchor or a few big anchors. You want to distribute things because you are going into something really soft, so you want to.
It was amazing, the brick we were, it was like, you do this and you have
A pile of dust on the floor.
dust.
Yeah.
So I said,
It sounds like an
"How does
air-dried
this
brick or
change
sun-dried
for
brick.
200 years with,
Nice hand formed, low temperature fired brick. Yeah. And yet, if you treat it right, it'll be around for another 200 years. So, you know. Yes.
I had a question also. You were talking about the injectable filler. You mentioned if there were voids after you've already done that, how do you go back in and access those voids?
We'll drill additional holes and inject if there's areas. Now, we don't do that usually if the voids are this big. It's usually if you've got an area void. But I'm sorry. How do you?
How much time do you have to do that, to find the voids and then?
Oh, it's not particularly time critical. You don't have to do
So
it
you're
while
not
things
trying
are
to be
wet.
homogeneous or all one piece at that time.
It's not going to be regardless because most of the time the voids that you're injecting are not perfectly monolithic and interconnected. You'll have voids here and then some mortar and then you'll have some more void. So we want to fill in all the gaps as much as we can and get it as solid as we can, but usually not monolithic in the sense of concrete where you don't want a cold joint. We're not, for one thing, we're not injecting the whole thing in one day. You can't because you do build up fluid pressures that would then actually push your walls apart. So we're usually injecting about 4 foot of height in a day, roughly, and gradually working around. So it's not something that's done all in one shot anyway. Other questions?
What are the outside limitations, outside weather limitations on your installations?
Well, the good thing about compatible injected fill is we actually want the walls to be wet when we inject them. So rain is not an issue because we'll actually flush out holes with water before we inject anyway. If the substrate is moist, it helps prevent shrinkage of the material that we put in there. There still is some Portland cement in it, so there's some tendency to shrink. We want to minimize that tendency. So wet is fine, but because it does have, again, some Portland cement in it, we need that to cure. We don't want it to freeze when it's wet. Obviously, that would be really bad. So low temperature can be an issue. The other good thing about CIF is we're putting this into the middle of a mass masonry wall generally. So the temperature we care about is not usually the temperature of the air, it's the temperature of the masonry around the material that's being injected. So unlike, formed concrete or something like that with metal or plywood forms, we can actually inject to some significantly lower air temperatures because those masonry walls, one of the things we love about the masonry walls is they have thermal mass and they hold their temperature for a while. So we're not as sensitive to air temperature swings. You know, even if it freezes overnight, for example, if the middle of that wall stays 40 degrees, which it probably will, we should be fine. So we're a little bit thermally protected by the wall that we're injecting into, generally speaking. So it's a nice advantage. So I need to hand it off to Andy. He's been waiting patiently.
Okay.
He's going to talk more about some anchors.
Okay. I think I passed an anchor around. We use these anchors. I'm sorry.
Sorry, go ahead.
Yeah, we use these anchors on jobs that require stabilization, of course. And here's an example of what you might see. This is a socked anchor, and I'll pass one of those around. Why the sock? Well, oftentimes we're trying to contain the injection material and trying to keep it in a certain area. So the sock has a tendency to keep the flow of the CIF together so that it doesn't run freely to every area that might be outside of that area. So different sizes.
Are you trying to pull the building post crack up?
It depends. I mean, that could be a structural matter. Most of the time, we're just going in and reinforcing certain areas of the different layers of bricks so that they're more or less solid. And again, CIF might be injected as well into the core of the anchor as well. So it does a few things. You can actually tie walls together with it. Matter of fact, I was in Philadelphia a couple of weeks ago. They were working on the Lutheran Theological Seminary, and I was at the top of a bell tower that had, the walls were actually out of plumb. So they were repairing certain areas, and there were some areas where we actually took anchors and anchored the top of the bell tower together on all four angles. So it can be used to hold things together, or it can also be used to be actually anchored into a wall as well. Okay. So there are different sizes and different spleens, we call them. Some are actually solid and some are hollow. And the hollow ones that I passed around might be used for injection purposes as well. And the choice of the fabric that we would use depending on what it is that we're working on, of course. Here's an example of dry coring. And again, why dry coring? When we're working on historic structures, water coring or water used for coring can damage the building. So the dry coring method is much safer. And this is what a core has been taken out of this wall, and the socked anchor was inserted and injected, and this is what you would see. And this would actually be cut off and repaired, of course, but this is just an example of what an anchor would look like after it's been injected. So there are many different methods. The masonry coring method utilizes a lot of computerized manual systems, and the heads themselves are a diamond bit head used for the dry coring method, mostly used on heritage masonry. So the ties and anchor reinforcement, the tapered anchor that I just passed around is a very unique anchor, and the reason why we call it a tapered anchor is because it's been actually engineered to actually be stronger than just a regular anchor that you might use. And if you try to pull on that, be careful, don't flip it over, there's salt in there, but if you try to pull up on that, it's virtually impossible to pull out because the taper end acts as a locking mechanism here, as you'll see. Also good to be used in shorter areas. A lot of the, I think in the pump stations in New Orleans needed taper anchors, and that's what was used there. Here's an example of what you might see where the taper anchor is dry cored and installed, and you only have a limited amount of area below in the foundation, and that's why the taper anchor is favored for that purpose. Again, that would be tying in the brick to the foundation itself. So here's an example of how we would dry core, and there's a bit that is used to create that tapering effect. You'll see that happen here.
It's very dramatic music too. If you feel that.
Yeah. And then the bit goes in and creates the tapered end, so that when we install the taper anchor and inject it, it holds it in place. Okay, we're going to talk about a couple of case studies here that involve injection and interior reinforcement with anchors as well. And we will look at the condition survey, the laboratory development of the CIF, which is exclusive to the project that we're working on. I handed out some of the little packets there. You'll notice, I'm not sure what page it's on, but you'll see where there's a page talking about the compatible injection fill and the different strengths that are that can be found. The protocol review is done by Atkinson Nolan, and the quality control inspection as well. So in this case, we had a structure in Baltimore, the American Urological Association headquarters, built in 1906. The facade itself was it was out of plumb, about 11 inches or so, and it was in danger of collapsing. So some of the things that we went in and were able to do to secure it after a lot of evaluation, we were able to go in and actually solidify the party walls and inject them so they could be strong enough for us to pin the facade back to them. And you'll see they were having a lot of moisture problems. Apparently there was some of the drains here had been pouring into the building for many years and just caused a lot of water infiltration. There were also some modifications that took place in this building that happened in prior years. They created a retail space at the bottom here, which really changed a lot of the load bearing of the structure there. So this is what the walls look like. Several of the walls I think we had to rebuild, but most often we will take the existing walls and inject them to solidify them so that they could be used to hold that facade that was actually falling on the face of the structure. And you'll notice here where the facade is here, and having gone in and made these party walls structurally sound again with our CIF, it allowed us to go ahead and use anchors to pin back the facade to the rest of the structure. And some of the socked anchors were used for that purpose here. You'll notice helical ties were also used on the face of the facade to tie the face back to this is stone, of course, and there was a brick backup here. So once after the interior walls were made sound, the structure was actually pinned back to the party walls.
Excuse me, are the helical ties grouted?
The helical ties, once they go in, we do the grouting around them, and if there are voids where the helical ties were, the CIF will in fact fill those areas too.
They're just twisted in place though?
They're just twisted into place, yes.
So there's no other way and then are they visible from the exterior?
They are not.
Okay.
Everything is repointed on the outside, so everything we do, you actually, you don't even know that we were there once after we're done with the project, and we'll talk more about that as we go in. The anchors are a little different because you have some other work to do to cover the anchors if they're done from the outside. Usually we keep a piece of the core and it actually goes back onto the face of that anchor. So this is what the structure looks like, and I've got a better picture. I was down there last week, matter of fact. I was driving through Baltimore and I didn't have a chance to put it back up there, but it is a sound building, holding tight. There are no problems with the building, but it was a choice that the building owner made because they didn't want to tear down the building. Case study number 2 happens to be the University of Missouri, the School of Journalism. It was the first school of journalism in the United States of America, built in 1908, renovated 100 years later, and there were 45-foot walls that were unreinforced. We, along with Atkinson Nolan, came into the project when it was actually halfway done. The load-bearing walls had been taken out of the structure, and it was a very dangerous situation. They were actually adding a floor to the structure and going even deeper into the basement to allow for that additional floor to take place, to be built. So there were certain things that needed to be done to actually structurally make this sound before they would take any other steps. And we were able to go in and do some testing, flat jack testing, which gave us indications of the shear strength of the walls. Some Lujan testing, which we'll talk about in a couple of frames here. So in the end, what ended up happening with the structure, as you can see here, there are no load-bearing walls, a very dangerous situation. The walls were actually diagonally stitched, and we'll see the next slide will show how that was done, using anchors similar to what we have here, along with injecting all of the walls of the building to create more of a monolithic structure so that it could withstand additional load. Again, a condition evaluation that shows what an actual flat jack test would look like in this case.
And there, by the way, the strengths you saw there in the middle column, 405 to 485 psi compressive strength. So again, pretty low compressive strengths.
Lujan testing gives us indications as to what the voided areas within a certain wall might look like. So water is inserted, and as it pours out, that's measured as to what the flow looks like, and that gives us indications as to what the how much flow might be taking place within the wall, whether it's suitable or not for injection. This is the diagonal stitching reinforcement method that I was talking about. It was developed by Dr. Fernando Lisi in Naples, and at the time it had only been used in a couple of parts of the world, in Europe, Iraq, and Japan. And so it was developed for this particular project for purposes of stabilizing all of the walls here. And as you can see here, the cross sections or the diagonal configurations you see here were all of the anchors that were actually inserted into the walls. Now don't forget, the walls were 3 or 4 bricks wide, so there was room enough for us to go in and create the diagonal stabilization of this building. And here as it stands, you'd never know that we were there. Actually, when you see this building today, it pretty much looks brand new, and most oftentimes people will question whether or not we did our job because it is an invisible process. Case study.
About vapor barriers, because when you have that airspace between brick wall and brick wall, then the masons put in a loophole to get the moisture out. But you're making it all solid. That's not a problem with.
I'll turn that over to Donald. That's a technical question.
So it depends on what the intent was. So most historic walls were not intended to function as cavity walls. So what you're describing, where there's a gap and weeps, is a cavity wall. For a cavity wall to really function properly, you also need to have some sort of flashing or something to push moisture out of the weep holes, especially above windows and doors and anything that interrupts things horizontally. Most historic masonry structures were not intended, even though there is a collar joint there that's often open, that there's a gap there. They weren't intended to function as cavity walls. They were intended to function as mass walls or barrier walls, where they're simply thick enough that if you spray water on the outside, if rain hits them on the outside, there's enough masonry there that it can't penetrate all the way to the interior before the rain event stops and starts drying out. There's just enough masonry to kind of absorb it. The problem when mass walls fail, when they fail to do their job, it's generally because there's interconnected gaps and voids and cracks where the moisture doesn't have to actually absorb through a solid mass. It can travel through cracks and gaps and voids from the exterior to the interior, especially when there's wind-driven rain and there's actually pressure pushing it that direction. So most historic masonry walls, from a moisture standpoint, perform much better when they are solid and free of gaps and voids than they do if there are irregular gaps and voids and cracks. So in answer to your question, in a modern structure, if we were to inject into a cavity that was intended to act as a drainage plane, it would be a really bad idea. We'd be changing the intent from something that drains and weeps to something that's then solid. Although we've done that in certain cases because of extenuating circumstances, but generally speaking, you don't want to block weeps when it's intentionally designed to work that way. Most historic structures are not designed to work that way. There's no weeps over windows and doors. There's no intentional flashing. There's no flashing at all.
And this material in any case acts like the mortar.
It
has
acts-
more of the properties. It's not waterproof. It's not
It's just
impervious.
solid. It absorbs, but it
So it's
doesn't
going to
block.
act like the rest of the masonry, dissipating, absorbing, distributing the moisture.
Exactly. Now, there are some cases, especially when we have fairly open continuous collar joints, and the primary purpose is water resistance. For example, up on Park Avenue in New York, the project that we just did, the 1601 testing, the storm-in-a-box testing, their entire concern was moisture infiltration. It was not a structural project whatsoever. It was just a 3-wide wall that moisture was getting through. And there's a fairly continuous collar joint there between the exterior wide and the interior wide. We actually put an integral water repellent into the injection material in that case to make it more repellent. Not, integral water repellent is not an epoxy or anything. It just makes the material less absorptive. So in that case, we actually were trying to keep it from getting beyond that collar joint for waterproofing purposes. So different scenarios call for different things, but generally speaking, we're not going in and injecting into a system that has weeps and flashing. We're injecting into mass wall systems.
The air conditioning, heating inside doesn't go through to the brick.
Well, you're opening all kinds of cans of worms here. So, so this is kind of a challenging issue because in the modern world of being green, a lot of people associate insulation with efficiency. And one of the things that people like to do to historic masonry walls is put a bunch of insulation on the inside of them, which can actually be harmful to the masonry if you do that improperly. But the way historic masonry mass walls generally work is they have a large thermal mass. We alluded to it earlier when we were talking about grouting. They warm up and cool down very slowly, and that thermal mass is energy efficient. It's just energy inefficient in a different way than we're used to calculating with our values, so people aren't as comfortable with it. By making it more solid, we're only making it more effective as a thermal mass, and we're reducing air infiltration and drafts and so on and so forth. The windows are someone else's problem. Someone else can make those energy efficient if they want to. But in terms of the wall itself, for a mass wall, you're only improving the energy efficiency if you make it more solid, because when it's not efficient, kind of like with moisture actually, same principle. When it's not efficient, it's usually because of air drafts that are actually passing through cracks and voids, as opposed to conductive heat transfer, if you will, across the thickness of the wall. It's massive enough to have thermal mass to resist them. Sorry.
So case study number three has to do with the New Orleans pump stations that we were called in to work on. along with the Army Corps of Engineers. They were in desperate need of stabilization at the time. A lot of diagnostics, non-destructive evaluation, and in situ testing, as Donald went over earlier, laboratory testing on what the type of CIF that we would be using on this for compatibility issues. The stabilization methods were helical anchors, like the ones I passed around, injection into the walls, and strengthening in a vertical and horizontal manner as well, you'll see. The extremely poor masonry conditions here that you see, this is a before picture, of course. Once the walls were injected, again, it created more of a monolithic wall, and that's what the intent was, to create more of a strong, strengthening the structure itself. The methods that were used, of course, the components, as I mentioned, the helical wall ties, CIF injection, the hollow stainless steel reinforcement rods that were used as well, and the tapered anchors that were used to actually engage and tie the brick to the foundation. Here's an example of a technician actually installing helical ties. They're actually drilled right into the brick so that they actually tie the withes of brick together to give the strength. And that would be done prior to injecting. An example of the technicians working at the top of the roof of one of the pump stations, and they are actually dry coring down into the foundation from this point. Some of the areas were anywhere from 50 to 80 feet high. Some of the machinery that is used, some of the more modern drilling technology that is available, and you'll see one of our technicians actually drilling. And again, we're looking at some of the anchors that were used, the taper anchor that I passed around, the little salt container. You'll see that here, and again, that was used for purposes of anchoring the actual brick wall. And here's an example of what it might look like when a technician is injecting one of those anchors at the top of the roof. The grout injection would actually travel down the anchor all the way down to the bottom. And again, some of these other tubes are used so that when the grout is rising up, he's actually using different hoses to pump the rest of the grout injection into the wall. So this is what the powerhouse, one of the pump stations looked like after we were finished here. You'll notice that the anchors actually were vertical and horizontal, and these were actually placed, they were actually drilled, dry cored, placed, and then injected. So the results and the conclusion of the case study here resulted in 11,000 square feet of wall area being injected, 42 cubic yards of our CIF compatible injection fill being injected. That came out to about 7% of what the wall volume actually was. 9,000 linear feet of stainless steel reinforcement bars, and there were no visible changes to the structure and no service interruptions. And that was a very big deal there because they were not able to shut these pump stations down. These pump stations are constantly running 24 hours a day to keep New Orleans dry. So that was a big factor in this whole project, finding that they found us, and the work that we do, actually we're able to work in areas that need to be continuously running. So that was a major factor in this project. So buildings are all strengthened and preserved, and you wouldn't even notice that we were there. I mentioned that earlier. Oftentimes, looking from the outside, it's not a visible thing that your eyes can see. So our certification is that the rejuvenated structure will perform as well as or better than a new structure built with excellent workmanship, utilizing similar materials, dimensions, and designs. each and every structure, masonry structure, can be saved. Are there any other questions for us, whether they're technical or having to do with, yes?
When you go to do the concrete, the injection process, typically a wall that needs that is going to be sagging or bone. Do you inject it to keep it in that condition, or do you try to straighten it first?
That's interesting. We got the same exact question yesterday. Everyone has that same thought. Typically, we preserve and strengthen in place. So we're going to tie it together, inject it, make it solid, make it strong, but not try to squeeze it back together. There are some situations where that can be done, and a lot of our anchors are threaded so that you can actually put a nut and a plate on it and try to tighten things up. But generally speaking, masonry is not a very ductile material. So if you try to squeeze it and deform it and bend it and so on and so forth, it's going to crack or worse. So generally speaking, we will stabilize in place, make it solid, make it structurally sound in place without trying to squeeze it back together. When we talked about the wall that was really badly bowed, the more badly bowed areas of those walls generally just have to be rebuilt in order to restore the out plane.
Yeah, you talk about how masonry is not that ductile, and yet it's attached to steel frames on these older buildings, and especially the solid masonry wall. And they didn't have expansion joints in these buildings over many feet. Some of these buildings are very large. And how do you deal with that when the inherent expansion and contraction of the structure is going to simply reintroduce new cracks?
Sure. So there's a couple different points in there. One, which is a question that we get a lot, especially from historic homeowners and other people with historic buildings, is my building doesn't have expansion joints. Should I put some in? Does it need it? Do we need expansion joints? Or if not, why not? Why does the brick building that was built 10 years ago in the corner have all these expansion joints and mine not? The basic answer to that is that the masonry material, historic masonry materials, are soft enough and flexible enough that they can actually absorb some of that movement, especially within the mortar joints, because the lime sand mortars are so soft they can actually compress and handle some movement, which is another reason why you don't want to put something really stiff and hard into a system like that, because you're then restricting that movement. So that's one aspect, is usually you don't actually need expansion joints in historic materials because they're soft enough to absorb movement. Where you have interactions with steel, things can get tricky. One of the big projects that we did recently in California was that configuration. It was actually clay brick and some very early 1920s concrete block, which is pretty rare to see concrete block that's that old, but clay brick masonry and concrete block with a steel frame as well, especially at a tower. And there were definitely some challenges in terms of dealing with that. One of the challenges, honestly, is we were trying to do reinforcing and that sort of thing, and the steel can kind of get in the way. So trying to get through walls that have steel in them can be pretty challenging. But in that case, the engineer actually wanted that steel to act compositely with the masonry around it. So we grouted solid against all the steel frame. Now, this steel frame was not exposed on the exterior face. It was completely enclosed. So from a temperature standpoint, there was much less risk of differential movement in that case. And it was a seismic concern, so the big thing was strength, ductility. So those can be challenging, but again, one of the best ways to deal with adding any kind of reinforcing or steel into a masonry structure is to get it well centered within the wall so that it's both thermally acting in conjunction with the surrounding masonry, and it's allowing the wall to work the way it originally was intended to work.
Any other questions? Yeah.
Well, a little lower on the scale from the things that you're doing, I do notice that all of the bricks that you're saving are in pretty good shape. I mean, they aren't falling apart.
Wow.
So
Maybe in the pictures we showed.
I mean, the wall might be, but the bricks look like they're okay. I didn't see anything that was fault. And so I wondered, is there anything new in terms of being able to save small brick? Or
Okay.
you just have to take it down, and never mind about your reinforcing, you don't have anything but powder there to put it in.
Sure. Yeah, that's a different kind of area, and
Yeah.
unfortunately, again, if you walk down the hall in this building, you will see along the base of the wall quite a few. I think I even saw a face that had recently spalled off on the floor. So a lot of spalled faces of brick. These types of repairs aren't intended to, because those are usually surface repair, surface items. These types of repairs, CIF and anchoring and so on and so forth, really aren't that well suited for
You
spalled
just have
brick.
to rebuild those areas pretty much.
Generally speaking, that's what you
Not
have to
much
do.
more.
You're talking about walls that have been painted though? Or were they painted first? and then
Well, it could be, but it could be just, I have an instance where there was just a lot of water being sucked up
Yeah.
from the ground where water was not well managed.
They didn't have drainage?
That's what it is along here.
Yeah,
It's just
and
called
it's
rising
just
damp is what we call it. So
Kinda
water
like this,
actually
you know.
is trying to migrate through. And frankly, the pointing job that was done on the outside doesn't help because you actually want the moisture to be able to come up through the wall and ventilate out, dry out to the exterior. When you fill those lime sand joints with Portland cement, the moisture path is then blocked to the exterior, so it's got to go to the
Stays in
interior.
brick, brick closes.
It gets more
So that's
saturated.
typically why you
doesn't
don't
flow.
want to paint brick and things like that also.
Exactly. You really want the brick. In fact, the way I usually describe it to help people envision it is lime sand mortar is essentially a poultice. It actually draws the moisture out of the surrounding masonry units, and it was intended to do that. It was intended to be somewhat of a sacrificial lamb to draw moisture out of the brick into the mortar and get it to the exterior, with the understanding that if there's freeze-thaw damage, etc., it happens in the mortar joints, and the mortar joints can always be repointed later and maintained. When you make the mortar the hardest, least permeable part of the wall, then your sacrificial lamb becomes the units, the brick units, which are much harder to repoint, as we're talking about.
Right.
You basically
I
have
just
to
wondered if
replace
there
them.
was any way to save those bricks. I keep thinking with all this magic material,
No.
something will come along that could penetrate that brick. I don't understand why it doesn't.
No, I mean,
The only thing that I've seen in the field that somebody was touting a few years ago was basically a structural harging, sort of like stucco in the wall, and it has a fibrous additive to it, and it is a masonry, it's a Portland-based product, and they were touting that you didn't even have to put mortar between your bricks, or it was designed for cinder block. So you'd stack your cinder block, like you'd stack any wall, and then you just parge the outside of it, and this particular parging had a tensile strength, which the CIF doesn't have a tensile strength to it, does it?
no, I mean, again, it's generally designed to be pretty compatible with what's around it, so the tensile strength is going to be comparable to what the masonry is, which is very low.
Right. So then you would do that, but again, if you use this kind of material and it has a high tensile strength, it may just take the brick apart, or it might have a flake in the face. You're familiar with what I'm talking about?
Yes, that's actually called surface bonded masonry in general when you do it in new construction, and it's not uncommon to see, especially in basement areas, people who parge the inside face of their wall with a very hard stucco or plaster or just a very hard mortar to try to kind of stop the deteroration that's happening in there.
Right.
That's a
that
kind of
okay thing
a
to do?
dangerous game because for one thing, you are then hiding whatever's happening behind there from your sight, which may make you feel better.
Oh, yeah.
But if it's still happening behind there, it's not actually better. And you're also, again, you're limiting the avenues for moisture to get out. So if you If you want to stop moisture, usually the back of the wall isn't the place you want to stop it. You want to stop it before it gets in the wall at the exterior. So I would say if you're going to go to effort of trying to keep water out, I would get out some shovels and try to do that on the exterior face, put in some drainage. You could even put in
We've
something
got
on the
this pretty
exterior
much
surface,
dried
but-
out, but now it's what to do
What to
from
do with
all
what's
those
left,
decades of the moisture sucking up into the brick.
Yeah, I mean, I would try to find a good salvage yard that's got some similar brick, and if it is it brick or is it stone there?
It's brick.
Okay. So find some similar brick and use a compatible historic type of mortar and rebuild. Yeah.
Even if
You
you
know,
put
the-
stucco over it.
The thing that I try to keep in perspective for people is, it's really horrible and it looks bad and it's very upsetting, but it's still probably lasted about 100 years or so if it's a lime sand mortar. If you make it last for another 100 years, I think you've probably done your job in terms of the repairs. So.
I'll take
Yes.
So I'm pretty amazed at what you do, but what are the costs involved?
You want price tags?
Yes.
Well, it depends. A lot of the repair work that we do tends to be on that we work on together tends to not be on residential units because it is a pretty expensive mobilization. You have to have pumps, you have to have mixers, you have to have people who know what they're doing. I don't know what a small project that you've done on recently is, but well, I don't know how you want to describe it. I know, yeah, but it tends to be a somewhat expensive process relative to slapping mortar on something or repair material on something, partially because it is specialized or specialized equipment, etc., and partially because there's not someone on every corner who does it, so you've got to get someone in who does it. But I don't know what you.
So
I shouldn't even talk.
I get
about
that question a lot, and oftentimes compared to rebuilding,
That's the big
I mean, it could be a third or a third to a half of what it would cost to rebuild. That's a typical assessment, I would say. Any other? Yes.
And also, room repairs are more of a long-term thing, it's not just a.
Correct.
For now, it's something you're
Because of the
passing on, and those structures that you're working on are to be there for a long time, not just to get through. this
absolutely,
generation.
and that's why concentrating more on historical, but not discounting the fact that it could be any structure that is in need of stability, structure stabilization. So, any other questions? I guess we're done. I think we're running over time here. Thank you all for coming. We appreciate your time. If you have business cards you'd like to leave with me, that'd be great. We're always available. We have our website at masonrysolutions.com for more case studies. Very, very interesting case studies. And you may be working on something that's similar to one of the case studies, and you can see how we actually follow the process of stabilizing those structures. So.
Thank you very much.
Thank you very much for having us. We appreciate it.